Welcome back. We are considering the case with three reservations. It's an interesting extension, and as you we are looking for the probability that exactly one of three reservations is canceled. And remember, the main point here is we have to think about like three-dimensional spaces. There are in total 8 different outcomes because there are two possible outcomes for A, two for B, two for C. So 2 times 2 times 2 possible outcomes in total. So there are 8 possible outcomes, and I'm going to list all of them like this. So A maybe so 0, 0, 0 means A is not cancelled, B not cancelled, C not. And cancelled, not. Not cancelled, not cancelled, cancel, not, cancel, not cancel, not cancel, cancel. So this is all the list of all the possible outcomes, and we are looking for, among these 8 possible outcomes, we are looking for the outcomes uh, that in which only one reservation is canceled. That's these three guys. So in the first one, the number of cancellation is 0, and in here 2, 2, 2, and 3. So exactly these three guys satisfy our event. So they are included in the event we are interested in. We are looking for the number of cancellations equals 1. And as I said, as you can see here, I only told you one cancellation happens, but I did not say who's the one canceled. What is canceled? I did not specify either it is A or B or C. So you have to think about three different scenarios. It could be A, it could be B, it could be C. So we are going to think about three different separate outcomes that satisfies our event. So the probability of our event can be written as the probability that A cancelled but B and C not, plus probability that B cancelled but A and C not, and plus probability C cancelled but A and B not. These are three different outcomes, and we are going to include those all three probabilities. And then each of the probability can be simplified, can be written as a multiplication of probabilities using statistical independence, because A, B, C are statistically independent with each other and they are connected by intersection. So you can replace it with multiplication. So probability of A cancellation, 0.1. Probability of B not cancelled, 90%. Probability C not cancelled, 90%. And similarly, 0 is replaced by 0.9, 1 replaced by 0.1. So in that way, you can calculate the probability of each outcome. But there are three outcomes. And what is interesting here is the probability of each outcome is the same, right? It doesn't matter it is A or it is B or it is C. The probabilities are always zero 0.1 times 0.9 squared. So 0.9 is multiplied twice and 0.1 is multiplied once. It's obvious because I said like A and B and C have the same distribution. We assume that probability of cancellation does not change across reservations. It is the same. Therefore, it does not matter so the probability does not depend on who canceled the reservation, right? A, B, C have the same probabilities. So in the end, it ends up as 3, which is the number of outcomes that satisfied that belonged to our event, times probability of a single outcome, right? Probability of single outcome if as if you knew who canceled, right? So this is the answer, and if you calculate this, the answer to this question is I don't know. I did not mark the correct answer. Please try to try try yourself. I'm sorry. I just got it. So C is the answer. The answer is C, 24.3%. As you can see again, this probability cannot be inferred from like by random combination of the numbers here. 3, 10%, 1 does not make up this number at all. So it's not easy to guess it. So you need to correctly understand the steps to get this probability. Okay, then let's think about these, compare these two cases, two answers. When you have two reservations, the probability of one cancellation equals this form. And probability of one reservation, one cancellation in three reservations case is 3 times this, right? These are our answers. And as you can see, the structure is quite similar. Structure on the right hand side is quite similar, and it consists of, you can split the right hand side into two parts. The first part and the second part. The first part, the number of outcomes in the event is 2 and 3. So there were 2 outcomes. There were total 4 outcomes, but among 4, only 2 are included in this event. And in 3 reservations case, there were 8 total outcomes, and among 8, 3 outcomes are included in this event. So 3 outcomes had 1 cancellation. On the other hand, this side, the last term, captures the probability of a single outcome. So obviously 0.1 is the probability of cancellation, and 0.9 is the probability of non-cancellation, probability of success and probability of failure. In this case, in 3 reservations case, you multiply success once and failure twice, because to have 1 cancellation out of 3, it means 1 is cancelled and the other 2 are not. So you have to multiply the probability of non-cancellation twice. That is what you can see from comparing these two answers, right? We are going to generalize them even more later, and it's not so straightforward. Let's study the last term first. It's more straightforward. The first part is less straightforward. So, as I explained, the second part was it came from this form. So you are using the multiplication rule to replace the intersection with multiplication, right? And that holds in 3 reservations case. And the main idea, the basic underlying idea is this. 0.1 is multiplied as many times as cancellations. In both cases, we consider the example of 1 cancellation. Therefore, 0.1 is multiplied only once. Cancellation happens only one of the reservations, and the other reservations are not cancelled, which has a probability 90%. So in 2 reservations case, 0.9 is multiplied once, and here twice, right? So 0.9 is multiplied as many times as non-cancelled reservations, right? And the final numbers do not depend on who cancelled. It depends. So these 2 are the same. These 3 are the same with each other, right? So probability of cancellation is the same for all reservations. Therefore, if you can calculate one of them, then you do not need to calculate the others. That is another simple pattern we can find from those two simple examples. So we came a lot. We learned a lot. We did a lot, and in simple, relatively simple examples, and still we have to go further. Like we are going to generalize. We are going to generalize that case to n reservations, n number of trials, n number of experiments, and still and p, the number of the probability is written as p, and then and also we are going to generalize the number of success, which equals to lowercase y. I'll simply call it y. So then from this setup, as I told you, success happens y times, and the other n minus y cases are failures. So therefore, success probability p multiplied y times to the exponent of y, and failure probability 1 minus p multiplied as many as times as n minus y, which is the number of failures. Make sense? Right? So there are n number of reservations, and we know y are cancelled and the other n minus y are not. So the cancelled, for each cancelled reservation, you have to multiply p. For each reservation not cancelled, you have to multiply probability 1 minus p. Then you will get this guy in the end. And remember, this is the probability of a single outcome when you know who cancelled, right? So what's missing? You just this part is a generalization of this. This colored part is generalized to this formula, right? But you like so even though the formula looks a little bit complicated, but its intuition is pretty straightforward. You multiply success probability and failure probability as many times as they happened. That's the key idea, right? So I'm missing coloring again and again. Anyhow, so yeah. And now we are going to study the other part, the number of possible scenarios. This part is even more complicated, and so we need further generalization. We are going to consider 4 reservations case. So now everything else is the same, but you have A, B, C, D. There are 4 cases, 4 reservations. And now I'm going to consider probability that number of cancellations equals 2, not 1, equals 2. We are going to apply the same rationale I told you earlier. So you can try this. It will be difficult. It does not matter even if you cannot answer it correctly, but I want you to try this. Try to apply the rationale you learned earlier to answer this question. Then you may be able to get the correct answer. Good luck, and I will see you in the next video.